5 miles, 10 minutes. No engine, no horse, no steam power, just gravity and water. A log placed in a wooden channel at the top of a mountain would travel 5 miles to the bottom in 10 minutes, reaching speeds of 60 miles per hour on the steep sections. This was faster than a train, faster than any vehicle of the era, and it required no fuel, no power source, nothing but the natural force of gravity pulling the log down the mountain and water providing a frictionless surface for it to slide on. The entire system was built from wood, a V-shaped channel constructed of boards, elevated on trestles over ravines, following the contours of the mountainside, carrying a continuous stream of water and logs from the cutting areas to the mills below. This was the log flume. And it was one of the most efficient transportation systems ever devised for moving heavy materials over difficult terrain. This was the American West in the late 1800s and early 1900s, and the mountain forests were being logged at an industrial scale. The problem was transportation. The forests were on mountainsides, thousands of feet above the valleys. The logs needed to get from the cutting areas to sawmills or railroad connections at lower elevations. You could haul them with horses or oxen, but that was slow, expensive, and limited by terrain. You could build railroads, but that required massive capital investment and constant maintenance. Or you could build a flume, a wooden channel that would use gravity to move the logs at speeds and efficiency that no other method could match. Could a wooden channel really carry logs at 60 miles per hour down a mountainside? Could you build such a structure 5 or 10 miles long over terrain that included steep grades, sharp curves, and deep ravines? And could you operate it safely when logs were traveling at speeds that made them nearly uncontrollable projectiles? The answer is yes. The evidence exists in photographs showing these incredible structures snaking down mountainsides, in engineering drawings preserved in lumber company archives, and in the documented production records showing millions of board feet of timber transported through flumes. Before we get to the flumes themselves, you need to understand the physics that made them work. Because this isn't just about building a water slide for logs. This is about precisely engineering a system that converts gravitational potential energy into controlled high-speed transportation. A log at the top of a mountain has potential energy proportional to its height and weight. A 1,000-pound log 2,000 feet above the valley has enormous potential energy. If you simply push it off the mountain, it would tumble and crash destructively. But if you provide a controlled channel for it to descend, you can convert that potential energy into kinetic energy, motion in a controlled way. The flume provides the channel, the water provides the low friction surface, and gravity provides the force. The engineering of a log flume started with surveying the route. Engineers would walk the mountainside from the cutting area to the destination, usually a sawmill or railroad connection. They'd use surveying instruments to measure elevation changes, map the terrain, and plan a route that maintained a consistent grade. The ideal grade for a log flume was about 8 to 12%, steep enough that logs would move quickly, but not so steep that they'd go out of control. The route had to balance several competing requirements. You wanted the shortest distance to minimize construction costs, but you also needed to avoid terrain that was too steep or too rough, and you needed to ensure water could flow continuously through the entire flume. Water flows downhill, so the flume had to descend continuously from start to finish. Any section that was level, or that rose even slightly, would stop the water flow and create problems. The construction of a log flume was a major undertaking. A 5-mile flume might use 500,000 board feet of lumber for the channel itself, plus additional timber for trestles and supports. All of this lumber had to be cut, milled to specifications, hauled to the construction site, and assembled. For a flume being built in remote mountain terrain, the logistics were challenging. The lumber might have to be hauled miles by wagon before construction could even begin. The construction process typically started at the bottom of the flume route and worked upward. This allowed the lower sections to be completed and tested, while the upper sections were still under construction. It also made sense logistically because materials could be hauled to progressively higher points as the construction advanced, using the completed lower sections as part of the access route. The basic structure of a flume was a V-shaped channel made from boards. The typical dimensions were 4 to 6 feet wide at the top, narrowing to a point at the bottom, with sides perhaps 3 to 4 feet tall. The boards were typically 1 to 2 inches thick, cut from whatever wood was locally available: pine, fir, cedar. The boards were assembled into sections with the joints sealed using oakum, a fibrous material similar to rope, driven into the cracks and sometimes coated with pitch or tar to make them watertight. The assembly technique for the flume channel required precision. The boards forming the V had to meet at the correct angle, typically 45 degrees from vertical, creating a 90-degree V at the bottom. If the angle was wrong, logs wouldn't settle properly in the channel. The boards were attached to a framework of crosspieces and supports that maintained the V shape and provided attachment points for the structure to the ground or to trestles. The framework itself was substantial. Crosspieces every 4 to 8 feet provided lateral support and maintained the channel shape. Longitudinal stringers ran along the outside of the channel, providing additional strength and serving as mounting points for the trestles. The entire assembly for a 10-foot section of flume might weigh several hundred pounds and require a crew of 4 to 6 workers to position and secure. The sealing of joints was critical. Water leaking from the flume was wasted water that might be needed downstream, and leaks could erode foundations and damage the structure. The oakum sealing technique involved packing the fibrous material into the gap between boards using a caulking iron, a chisel-like tool driven with a mallet. The oakum would swell when wet, creating a tight seal. For joints that were particularly prone to leaking, the oakum would be coated with hot pitch that would harden and provide additional waterproofing. The grade calculation for the flume route was sophisticated engineering work. The engineers needed to know the exact elevation at multiple points along the route. They'd use surveying equipment, transits, and leveling rods to measure elevation changes to within a few inches over distances of hundreds of feet. From these measurements, they'd calculate the average grade and identify sections where the grade was too steep or too gentle. Where the natural terrain didn't provide the desired grade, they had to modify it. Too steep a section would be made gentler by building the flume on a diagonal rather than straight down the slope, adding distance but reducing grade. Too gentle a section might require cutting into the hillside to increase the grade or building a trestle to elevate the flume. In some cases, the flume would zigzag across a mountainside, adding miles to the total length, but maintaining a workable grade. The V-shape was critical to the function. When a log entered the flume, it would settle into the bottom of the V, held in place by gravity. The water would flow around and under the log, providing a lubricating layer that dramatically reduced friction. The log would be partially floating, partially sliding on the thin film of water. This allowed it to move much faster than if it were simply sliding on wood against wood. The depth of water in the flume was another engineering parameter. Too little water and logs would drag on the bottom, wearing through boards and slowing down. Too much water was wasteful and could cause logs to float too high, potentially allowing them to tip or jump out of the channel on curves. The ideal water depth for most flumes was about 6 to 10 inches when no logs were present. With a log in the channel, the water would be displaced and rise around the sides of the log, but the log itself would ride on a thin film of water at the bottom of the V. The water flow rate had to be calculated to match the expected log throughput. If you were sending 50 logs per hour through the flume, you needed enough water flow to lubricate each log adequately. The calculation involved estimating friction coefficients, surface areas, and flow rates. Too little water and logs would jam. Too much water was wasteful and could erode the channel or damage structures downstream when the water dumped out at the end. The intake structure at the top of the flume was often an elaborate installation. It would include a settling pond to allow debris to drop out of the water before entering the flume. Screens or grates would catch branches and other material that could clog the flume. Flow control gates allowed operators to adjust the water volume, and there would be an overflow system to handle excess water during high flow periods, typically a spillway that diverted water away from the flume to prevent flooding the channel. The water supply for a flume was often as complex as the flume itself. The flume needed a constant flow of water, typically hundreds of gallons per minute for a large flume. This water came from streams, springs, or reservoirs built specifically to supply the flume. At the top of the flume would be a water intake, a structure that diverted water from the source into the flume channel. The intake had to be designed to prevent debris from entering the flume while allowing sufficient water flow. The grade of the flume determined the speed of the logs. On gentle grades of 5 to 8%, logs might move at 10 to 15 miles per hour. On steep grades of 15 to 20%, speeds could reach 40 to 60 miles per hour. The engineers had to design the route to avoid sustained steep sections where logs would accelerate out of control. The solution was to vary the grade, steep sections to build speed, followed by gentler sections where logs would slow down, then steep sections again. The curves in a flume required special engineering. A log traveling at 50 miles per hour has tremendous momentum. If the flume makes a sharp turn, the log wants to continue straight and will slam into the outer wall of the curve with great force. The engineers dealt with this by banking the curves, elevating the outer wall so the log would ride up the bank as it went through the curve, similar to how a car uses a banked curve on a racetrack. The banking had to be calculated based on the expected speed of logs through that section. The trestles that supported the flume over ravines and rough terrain were engineering challenges in themselves. A flume might need to cross a canyon 100 feet deep. The trestle supporting the flume at that point had to carry not just the weight of the wooden channel, but also the weight of water, which is heavy, at about 8 pounds per gallon, plus the weight of logs traveling through at high speed. The dynamic loads from fast-moving logs could be substantial. The trestle design had to account for all these forces. The construction techniques for flume trestles were similar to railroad trestle construction: vertical posts supporting horizontal beams, with the flume channel resting on top. But flume trestles had additional challenges. The flume had to maintain its precise grade across the trestle. The channel had to be watertight even as the trestle flexed slightly under load. And the entire structure had to be built in locations that were often difficult to access. One of the most famous log flumes was the V-Flume, built by the Sierra Flume and Lumber Company in California in the 1870s. This flume ran from the forest near Lake Tahoe down to the Carson Valley, a distance of about 15 miles and a vertical drop of about 1,700 feet. The flume crossed numerous ravines on trestles that were over 100 feet high. At its peak operation, the V-Flume transported over 80 million board feet of lumber per year, equivalent to about 16,000 large trees. The construction of the Sierra V-Flume took 2 years and cost approximately $100,000, about $3 million in modern currency. The flume used over 2 million board feet of lumber for its construction. But once completed, it could transport logs at a fraction of the cost of any other method. A log that might take a day to haul by wagon could travel through the flume in less than an hour. The Sierra V-Flume was built in the summer of 1870 through 1872. The construction crew numbered about 200 workers at peak, including carpenters, laborers, and specialized workers like surveyors and iron workers who fabricated the metal hardware for connections and joints. The route followed Clear Creek Canyon for much of its length, which provided a natural grade and a source for flume water. The most spectacular section of the Sierra V-Flume was the Kings Canyon Crossing, where the flume spanned a ravine on a trestle that was 120 feet high at its center and over 300 feet long. This trestle required approximately 50,000 board feet of lumber and took 3 months to build. The construction was done by workers standing on scaffolding hung from the sides of the canyon. The danger was extreme. Several workers fell during construction, with at least 2 falling to their deaths. The operational statistics of the Sierra V-Flume are well documented. In 1876, the peak year of operation, the flume transported 92 million board feet of lumber, about 18,300 large logs. The flume operated about 10 months per year, shutting down during winter when snow and ice made operations impossible. During operating season, the flume ran about 12 hours per day. Workers would feed logs into the top at a rate of about 1 log every 2 minutes during peak periods. The logs would travel the 15 miles in approximately 45 minutes to an hour, depending on their size and the water conditions. Another notable flume was the Bricks Flume in Washington, built in the 1890s. This flume was about 8 miles long and descended about 2,000 feet from the cutting areas to the Snohomish River. The flume included several spectacular trestle sections, including one that crossed a ravine at a height of 150 feet. The Bricks Flume operated for about 20 years, transporting millions of board feet of lumber before being replaced by a logging railroad. The Bricks Flume was remarkable for its steep grade. Once portions of the flume descended at 15 to 18% grade, much steeper than typical. On these steep sections, logs would accelerate to speeds estimated at 70 miles per hour or more. The engineering challenge was controlling these speeds. The flume builders used a technique called friction blocks, wooden blocks mounted in the channel that would drag on the logs slightly, creating friction to slow them down. The blocks had to be replaced frequently because they wore down quickly from the high-speed contact. The Redwood Empire Flume in Northern California, built in 1885, was one of the longest flumes ever constructed. Over 20 miles from the cutting areas in the Coast Range to the town of Willits, the vertical drop was approximately 3,500 feet. This flume was built specifically to transport old-growth redwood logs, some of which were 6 feet in diameter and weighed several tons. The challenge of moving such large logs required the Redwood Empire Flume to be built to extraordinary dimensions. The channel was 8 feet wide at the top rather than the typical 4 to 6 feet. The sides were 5 feet tall. The water volume required was massive, over 1,000 gallons per minute at peak flow. The flume consumed about 2,500 gallons of water per log transported, which meant the water source had to be carefully managed to ensure adequate supply. The Big Creek Flume in Montana, built in 1902, demonstrated a different approach to flume engineering. Rather than building a single long flume, the Big Creek system used a series of shorter flumes connected by transfer points where logs would be removed from one flume and loaded into another. This allowed the engineers to optimize each flume section for its specific terrain rather than trying to maintain a consistent grade over the entire route. The system included 5 separate flume sections totaling about 12 miles, with 4 transfer points. Each transfer point had a holding pond, where logs from the upstream flume would collect and workers would feed them into the downstream flume at a controlled rate. The advantage of the segmented system was that each flume section could be optimized independently. A steep mountain section might have a flume with heavy friction control to manage speed. A gentle valley section might have a flume with minimal friction and high water flow to maintain momentum. The disadvantage was the labor required at the transfer points. Each one needed workers to manage the log flow, adding to operating costs. The Priest Lake Flume in Idaho, built in 1906, incorporated an innovative feature, a log elevator. At one point in the route, the flume had to cross a ridge where the natural terrain rose slightly. Water couldn't flow uphill, so a traditional flume wouldn't work. The solution was to end the upstream flume at the base of the ridge, use a cable-operated elevator to lift logs about 100 feet vertically, then start a new downstream flume on the other side of the ridge. The elevator was powered by a water wheel driven by the flume water itself. This allowed the flume to maintain its route while crossing terrain that would otherwise have required a long detour. The operation of a log flume required constant attention and maintenance. Workers called flume tenders would walk the flume daily, looking for damage, clearing debris, and making repairs. A flume tender's territory might be a mile or two of flume. They'd walk it every day, examining the channel, the trestles, the water flow. They'd carry tools, hammer, saw, nails, to make minor repairs on the spot. The damage to flumes came from multiple sources. Logs traveling at high speed would occasionally slam into the sides with enough force to crack or break boards. Heavy logs might settle too deep in the V and drag on the bottom, wearing through boards. Debris, branches, bark, shavaks, would accumulate at certain points and had to be cleared. In winter, ice could form and damage the channel. In summer, the wood would dry and shrink, opening gaps that needed to be sealed. The most dangerous problem was a jam. If logs were fed into the flume too close together, they could pile up, especially at curves or where the grade changed. A jam in a flume was serious. The water would back up behind the jam, potentially overflowing and damaging the flume. The weight of logs piling up could break the channel or collapse a trestle. And clearing a jam was dangerous work because the logs were under tension, held by friction, and releasing them could cause a sudden, violent movement. The flume tenders who had to clear jams developed techniques for doing it as safely as possible. They'd approach from below the jam if possible. I'm using PVs, hand tools with a hooked arm, to pry logs loose one at a time. Sometimes they'd have to climb onto the jam itself to reach logs that were key to the pile. This was terrifying work. You're standing on unstable logs in a flume with water rushing around them, knowing that if the jam breaks suddenly, you could be swept away or crushed. There are documented cases of flume tenders being killed clearing jams. In 1893, a tender named William Morrison was clearing a jam on a flume in Oregon. The jam broke while he was on it. Morrison was swept down the flume, carried a quarter mile at high speed, before the flume made a sharp curve and he was thrown out. He fell about 60 feet and died from the impact. His body was found at the base of the flume trestle. The lumber company paid for his burial and gave his widow $50. Operations resumed the next day. The speed of logs in a flume was both the system's greatest advantage and its greatest danger. A log traveling at 60 miles per hour covers 88 feet per second. At that speed, there's no time to react if something goes wrong. If a log jumps the flume, comes out of the channel, it becomes a massive projectile. A 1,000-pound log flying through the air at 60 miles per hour will destroy anything it hits. The worst documented flume accident occurred in California in 1897. A section of flume about 3 miles from the top had developed a crack that went unnoticed during inspection. As logs passed through, the crack gradually worsened. Finally, a particularly large log, estimated at 1,500 pounds, hit the damaged section at high speed and broke through the flume wall. So the log and the rushing water tore a 30-foot section of flume apart. The logs behind continued coming at speed and piled up at the break. The weight of the pile-up caused the trestle to collapse. 20 workers were on or near the flume when it failed. 7 were killed, some crushed by logs, some caught in the collapse of the trestle, one swept away by the flood of water. The flume was out of operation for 3 weeks while repairs were made. The men who worked on log flumes were a specialized workforce. Flume tenders needed to understand the system, to recognize problems before they became critical, and to work alone in remote locations. The pay was decent, $2 to $3 per day, but the work was constant and the responsibility was significant. A flume tender who missed a developing problem could cause an accident that killed workers and damaged expensive infrastructure. Among the flume workers was a man named Samuel Chen, a Chinese immigrant who worked as a flume tender on the Hobart Flume in California from 1886 to 1903. Chen's story is preserved in the records of a lawsuit he filed against the lumber company after being injured. The court documents include his testimony about his work and the conditions. Chen testified that he was responsible for a 2-mile section of flume that included a major trestle crossing. He walked his section every day, examining the flume for damage. He described finding cracks, loose boards, debris accumulation. He would make repairs using materials cached at small supply sheds along the flume. When he found damage, he couldn't repair alone. He would notify the superintendent, and a repair crew would be sent. In 1901, Chen was clearing a jam when the log shifted. His leg was caught between 2 logs. The pressure crushed his leg. Other workers pulled him free and carried him 5 miles down the mountain to the nearest settlement. A doctor amputated his leg below the knee. Chen sued the lumber company for compensation, arguing that the jam had been caused by the company sending logs down too fast and too close together. The court ruled in favor of the company, finding that Chen had assumed the risks of the work. He received no compensation. He worked various jobs after his injury, but never again made the wages he'd earned as a flume tender. Another documented flume worker was Thomas McBride, a Scottish immigrant who worked as a flume superintendent on the Trinity River Flume in California from 1895 to 1910. McBride's letters to his brother in Scotland, preserved by family members, provide insight into the management and operation of a large flume system. From a letter dated June 1897, I am responsible for the operation of 12 miles of flume, carrying logs from the cutting areas to the mill. I supervise 8 flume tenders and a maintenance crew of 6 workers. The work is constant. Something always needs repair. Yesterday, a trestle section showed signs of settlement. We had to shore it up immediately to prevent collapse. Last week, a major jam required 2 days to clear. This morning, I found a crack in the channel that could have caused a serious break, and we are making repairs now. McBride's letters also describe the financial pressure. The mill demands constant flow of logs. Any interruption in flume operations costs the company money. I am under pressure to keep the flume running at maximum capacity, but pushing too hard increases the risk of jams and accidents. I must balance production demands against safety. It is a difficult position. In a letter from September 1902, McBride describes a fatal accident. We lost a worker last week. Marcus Swenson, a flume tender I had known for 6 years. He was riding a log down the flume despite company rules forbidding it. The log hit a curve too fast and threw him out. He fell 60 feet from a trestle and was killed instantly. I had warned him many times about riding the flume. He told me he couldn't resist. The walk down would take 2 hours, but the ride took 20 minutes. Now he is dead, and his widow has 3 children to support. The company accepts no responsibility. I wrote to his widow expressing my sorrow, but could offer no compensation. Another flume worker whose story survived is James Wu, a Chinese laborer who worked on flume construction in Oregon from 1888 to 1895. Wu's account was recorded by a missionary who interviewed him in 1910. According to the missionary's notes, Wu described the construction work as extremely demanding. Wu stated that he worked 12-hour days, 6 days per week, for wages of $1 per day, significantly less than white workers doing the same work. He described carrying lumber, assembling channel sections, working on trestles at heights that terrified him. He stated that 5 Chinese workers were killed during the 2 years he worked on one particular flume project. 2 fell from trestles, 1 was crushed by lumber, 2 drowned when a partially completed flume section collapsed and they were swept away by the water. Wu also described discrimination. The white workers were paid more for the same work. We were given the most dangerous jobs. When accidents happened, the company did not care if Chinese workers died. Our families received nothing. If a white worker died, the company might pay his family $50 or $100. For Chinese workers, nothing. The missionary's notes conclude, Mr. Wu eventually left flume work and found employment as a domestic servant in Portland. He stated he would never return to flume work, despite the lower wages of domestic service. He said, better to live poor than die rich. A 4th documented worker was Eric Lindstrom, a Swedish immigrant who worked as a flume tender in Washington from 1900 to 1918. Lindstrom kept a detailed diary that was donated to a historical society by his grandson. The diary entries provide daily accounts of flume tender work. From May 3, 1904. Walked my section before dawn. Found several boards split from yesterday's heavy log traffic. Replaced them using stock from the supply shed. Cleared debris from 2 sections where branches had accumulated. Water flow is good. No jams today. From August 17, 1906. Heavy rain last night. Creek running high. Water volume in flume is excessive. Worried about overflow damaging the channel. Walked to the intake to check flow controls. Adjusted the gates to reduce flow. I walked the entire section looking for damage from the high water. Found one section where water had overflowed and eroded the foundation. Placed sandbags to stabilize. Will need proper repair when weather improves. From November 22, 1908. Cleared a major jam today. 15 logs piled up at the curve near mile marker 4. Worked alone for 3 hours using PV to pry logs loose. Dangerous work. The pile shifted twice while I was working on it. Nearly caught me. Finally got the jam cleared. Logs flowing normally now. Exhausted. Lindstrom's diary also records his observations about flume riding. The workers continue to ride logs despite knowing the danger. I have seen close calls, men nearly thrown from logs on curves, logs hitting debris, and men barely jumping clear in time. When I have forbidden riding on my section but cannot enforce it when I am not present, the temptation is too great. The alternative is a 2-hour walk. In a later entry from March 1915, Lindstrom describes a close call. I rode a log today despite my own rules. I was at the top of my section at the end of the day, exhausted from clearing 2 jams. The thought of walking 2 hours was unbearable. I selected a large stable log and rode it down. It was terrifying. The speed on the steep sections made my heart race. The log bounced and shifted. I nearly fell twice. When I reached the bottom, my hands were shaking. I have ridden before, but this time I truly understood the danger. I will not do it again. The technique of riding logs down flumes developed despite being explicitly forbidden by lumber companies. Workers realized that riding a log through the flume was much faster than walking along the flume or hiking over the mountain. A flume tender whose territory was 2 miles from the base could ride a log down in 10 minutes rather than hiking for an hour. The temptation was irresistible despite the obvious danger. Riding a flume was terrifying. You'd select a large, stable log. You'd position yourself on top, usually sitting or crouching. Then the log would enter the flume and accelerate rapidly. On steep sections, you'd be traveling at 40 to 60 miles per hour, crouched on a log that's bouncing and rolling in a wooden channel with water spraying around you. If the log hit a curve too fast, it could throw you off. If it hit debris or another log, you could be crushed. If you lost your balance and fell into the flume, you'd be swept away and could drown even in the shallow water. Despite these dangers, flume riding became common among workers. Some became skilled at it, learning to shift their weight, to control the log through curves, to judge when a log was about to hit an obstacle and jump clear. Others were less skilled and paid the price. As mentioned earlier, between 1892 and 1920, an estimated 200 to 300 workers were killed riding flumes, with hundreds more injured. The lumber companies posted signs forbidding flume riding. They fired workers caught doing it, but they couldn't stop the practice because the incentive was too strong. A worker at the top of the mountain at the end of a shift faced a 3-hour hike down or a 20-minute flume ride. Most chose the ride despite the danger. While the economic efficiency of log flumes was remarkable, the cost to transport 1,000 board feet of lumber through a flume was about 10 to 20 cents, compared to $1 or more for wagon hauling. For a large operation transporting 10 million board feet per year, the savings were enormous. The Sierra V flume, with its construction cost of $100,000, paid for itself in less than 2 years through reduced transportation costs. But flumes had limitations. They only worked where there was sufficient vertical drop. You needed gravity to make them function. They required a reliable water supply, which wasn't always available. They were expensive to build and maintain. And they were vulnerable to damage from accidents, weather, and wear. So most flumes had an operational lifespan of 10 to 20 years before they needed major rebuilding or replacement. The maintenance cost for a flume could be substantial. A 5-mile flume might require 2 or 3 full-time flume tenders plus periodic major repairs. The lumber company operating the Sierra V flume spent approximately $10,000 per year on maintenance, about 10% of the original construction cost annually. But even with these costs, the flume was more economical than alternatives. The decline of log flumes came with the development of better logging railroads and later, motor trucks. Logging railroads could operate in terrain where flumes weren't practical. They could haul logs uphill as well as downhill, and they could carry loads in both directions, bringing supplies up the mountain and logs down. By the 1920s, most new logging operations were using railroads rather than building flumes. The motor truck finished off the remaining flumes. By the 1930s, logging trucks could navigate mountain roads and haul logs efficiently. They offered flexibility that flumes couldn't match, the ability to change routes, to access different cutting areas, to operate in any terrain. The last commercial log flume in the United States probably ceased operations in the 1940s or early 1950s, though some small operations may have used them later. Today, very few flume structures survive. Most rotted away or were dismantled for salvage lumber. A few sections have been preserved as historical curiosities. The remains of the Sierra V flume can still be seen in places, sections of water-stained boards, the foundations of old trestles, metal hardware rusting in the forest. Walking these sites, you can trace the route of the flume and imagine the logs rushing down at speeds that seem impossible for a wooden structure. The engineering achievement of log flumes deserves recognition. These were precision-built structures designed to convert gravitational potential energy into controlled high-speed transportation. They required understanding of fluid dynamics, structural engineering, and material science, all applied with the tools and knowledge available in the late 1800s. The fact that they worked, that they could safely transport millions of board feet of lumber at speeds exceeding any other transportation method of the era, demonstrates sophisticated engineering. The workers who built and maintained these flumes, the construction crews who assembled millions of board feet of lumber into precise channels snaking down mountains, the flume tenders who walk their sections daily looking for problems, the workers like Samuel Chen who were injured doing dangerous maintenance work, they created infrastructure that was critical to the lumber industry for decades. They did it in remote mountain locations, often in difficult weather, with crude tools and minimal safety equipment. The log flume represents a specific moment in industrial history. A brief period when gravity-powered transportation was the most efficient option for moving heavy materials over mountainous terrain. The technology was simple in concept, a wooden channel and water, but sophisticated in execution. The flumes worked because engineers understood the physics and workers could execute the demanding construction and maintenance. They transported billions of board feet of lumber. They saved millions of dollars in transportation costs. They enabled logging operations in terrain that would otherwise have been inaccessible or economically marginal. And then they were abandoned, replaced by railroads and trucks, left to rot in the forests. The wooden channels deteriorated. The trestles collapsed. Within a generation, most flumes were gone, leaving only traces, a few preserved sections, old photographs, engineering drawings and archives, and the stories of the men who built and operated them. The next time you see a modern log truck hauling timber down a mountain highway, consider that 120 years ago, those logs might have traveled down the same mountain at 60 miles per hour in a wooden flume. No engine, no fuel, just gravity and water and precision-built wooden channels that could sustain those incredible speeds day after day. Consider the engineering required to make that work. Consider the workers who maintained the system, who cleared the jams, who sometimes rode the logs despite knowing it could kill them. And consider that this entire transportation system has been almost completely forgotten, known today mostly as a footnote in logging history rather than as the engineering marvel it actually was. 5 miles in 10 minutes, 60 miles per hour, 1,000 pounds of wood flying down a mountainside in a channel built from boards, controlled only by the V shape and the rushing water. It sounds impossible, but it happened. Every day for decades in logging operations across the American West. The log flumes were real. They worked, and they represent what could be accomplished when engineers understood physics and workers could execute demanding construction in impossible terrain.